Hi everyone, I'm Subramonyam, and today I'm going to talk about our VIS23 paper on the gaps in generalizability of VIS4ML research. This work is in collaboration with Jessica Hullman from Northwestern University. Consider the ImageNet challenge. Winning models boast top-tier performance on this dataset, identifying objects with near-human accuracy. But take one of these models and apply it directly to, say, medical imaging or satellite imagery without any fine-tuning. Of course, the performance drops dramatically. Why? Because every dataset, every domain has its nuances. Yet, when we talk about visualizations that aid our understanding and interpretation of these machine learning models, we often postulate that visualizations designed and tested for specific scenarios are generalizable across other models and datasets. We have all seen this impressive demo of the Google Facets tool where they spotted a frog mislabeled as a cat in a dataset containing 60,000 images across 10 classes. The design hypothesis is that providing a confusion matrix view of ground truth and predicted labels will allow experts to identify particular kinds of misclassifications in image data. But can we visually explore and arrive at a similar insight using a completely different dataset? And how critical is the identification of these misclassifications to the success of the model? Of course, the nature of the data, the extent of expertise required, as well as the misclassifications best revealed by this visualization all determine whether a VIS4ML contribution can be applied to other real-world ML pipelines. In this work, we closely examine the generalizability claims made in visualizations for machine learning research contributions. We broadly define generalizability as the alignment between the general claims made about the effectiveness and applicability of VIS4ML contributions and the quantitative or qualitative evidence presented to validate those claims. For our qualitative analysis, we started with a list of papers in a recent survey of visual analytics for machine learning and also conducted keyword search to collect an initial set of 414 papers pertaining to visualizations for ML. We then selected papers that specifically focused on human-in-the-loop tasks. They provided concrete design goals and also supporting evaluation, and they also claimed to improve the ML modeling pipeline. This resulted in a set of 76 papers, of which we sampled 52 for our qualitative analysis. Each author independently analyzed 5 papers to establish a codebook. Utilizing this codebook, we individually examined half of the papers in our collection with a thorough reading and coding approach. After several discussions, we consolidated our observations and synthesized gaps in VIS4ML research. Broadly, our findings encompass 4 unique facets of human-in-the-loop machine learning: the depth of human expertise and prior knowledge, the data and modeling tasks demanding human interventions, the data sets and models themselves, and the visualization tools facilitating human-in-the-loop ML. Let's start with findings about human roles and expertise. In our coded papers, approximately 77% actively collaborated with experts during the visualization system design. This collaboration typically involved regular meetings, interviews, iterative design, and evaluation, and in 3 instances, participatory design. Further, half of these papers collaborated with machine learning experts, 9.6% of 5 papers engaged domain experts, and 2 involved data scientists. Notably, 3 papers collaborated with both machine learning and domain experts, and across these systems, participant count varied from 2 to 20, with 2 papers identifying the authors as the primary experts. Now, though formative studies involving experts are crucial for the design of human-in-the-loop visualizations, almost all papers we reviewed lacked comprehensive details on study protocol, recruitment strategies, but more importantly, specific participant expertise and characteristics of their skills that influenced the tool design. In analyzing the design considerations from formative need-finding studies, we sort of identified these underlying implicit assumptions about experts' pre-existing knowledge and competencies. About 21% of the papers assumed that expertise in machine learning, including conceptual grasp of specific models, hands-on experience in training them, and proficiency in interpreting model metrics and performance. Approximately 27% of papers also assumed data proficiency, implying familiarity with certain data sets, a contextual understanding of data and labels, as well as like the ability to gauge data instances and class relevance. And another 15.3% of papers assume domain expertise ranging from general understanding like how language works to domain-specific knowledge. This includes contextualizing model decisions, distinguishing between effective and ineffective model behavior, and anticipating domain-specific repercussions of model inaccuracies. Some papers also assume tacit knowledge about human-in-the-loop ML tasks from past experiences of these experts, along with diagnostics and reasoning skills like hypothesis testing and counterfactual reasoning. However, many papers did not provide clear descriptions of the prerequisite knowledge or skills for using the visualizations, nor did they clarify the nature of the inputs integrated into this system. Now let's briefly talk about the ML components that underpin these visualization tools. From our analysis of the modeling techniques, as well as the data sets cited in the system usage and evaluation examples, we observed a prevalence of well-recognized data sets like ImageNet, CFAR10, MNIST, and the UCI repository. Regarding modeling, a significant portion centered on neural networks, with 38.5% papers highlighting CNNs. Many papers posited that leveraging well-established data sets strengthened their findings. However, some noted the importance of tools being supportive and evaluated on data that truly resonates with experts. For instance, while using popular data sets like MNIST might offer robust verification, its simplicity may yield limited insights on diagnosis and model enhancements. Papers also asserted claims of generalizability, suggesting that their proposed combination of visualizations and interactivity with some additional engineering can be applicable to other scenarios. A third set of findings are about the capabilities of VIS4ML tools in facilitating human-in-the-loop machine learning. Nearly all papers highlighted the importance of VIS4ML solutions, pointing to current machine learning deployment challenges and advocating for a human-centric approach to machine learning. As shown here, the human-in-the-loop tasks span 7 main categories, including being able to interpret model behavior, correct model errors, prepare the training data, feature engineering, selecting modeling techniques, determining model configurations, as well as overseeing model training. Though most VIS4ML tasks outlined as specific, like class or model comparisons, in some papers we noticed that the tasks are vaguely defined, such as exploring details or understanding model behavior. Further, while numerous papers anchor their goals in metrics like model performance, effort, or the diversity of modeling traits, the exact definitions of these metrics and their origins, whether they're from formative studies or just predetermined by researchers, are often left ambiguous. In the example use cases provided in most papers, they showcased how the visualization aids human-in-the-loop tasks, emphasizing the nature of insights that the human derived. From coding and clustering these insights, we identified 6 distinct categories of insights generated through VIS4ML. This includes being able to glean into specific inference mechanisms, like understanding that the car window as a concept is pivotal for vehicle classification, or finding evidence of error, as shown in Data Debugger with overlapping classes for jacket and downcoat in the scatter plot, or being able to pinpoint root causes of errors using visualization, such as in DeepEyes, where the same filter is activated across different classes, or being able to just validate correct behavior using visualization. For instance, in Summit, the model distinguishes between black bear and brown bear based on color, or guiding perception of data space and modeling decision like feature selection, as well as comprehending model performance as influenced by expert decisions. Based on the insights presented in the paper, we coded any action described as taken by the human expert. In our set, 42 papers highlighted actions that were taken based on the insights gained. 27 papers elaborated on the specific actions an expert carried out after using the tool. In some instances, they even presented results after retraining the model due to an implemented change. Furthermore, 19 of these papers went a step further. They quantified the impact of these actions, often showcasing enhancements in accuracy or reductions in error. However, it's essential to note that 25 papers took more of a speculative approach. The authors hypothesized about potential actions that could be made or presented them as avenues to explore in the future. A critical observation here is that over half of the papers in our review did not offer concrete evidence about the effects of integrating VIS4ML systems into the ML pipeline. Lastly, we briefly describe our findings about visualization tools implementation and evaluation. Previous taxonomies have already covered specific visualization and interaction techniques observed in our analysis, so here we zoom into distinct implementation aspects, particularly emphasizing post-hoc interpretability methods. While most papers laid out desiderata for tool development, like aligning with established modeling practices or supporting varied work environment, the clarity regarding these requirements in the implementation was less clear. A recurring theme was the use of dynamic algorithms and visual approximations. Many papers utilize dimensionality reduction techniques like PCA, UMAP, and MDS, or projection techniques like TSNE. However, the application of VIS4ML tools hinges on transparently conveying the hyperparameters and details about the tuning process, and papers varied considerably in the extent to which they specified such information for dynamic visualization algorithms like TSNE, clustering approaches, or other optimizations. To understand the evaluation practices in VIS4ML, we used the established taxonomy by Eisenberg et al. For instance, every paper employed visual data analysis and reasoning, often with the use of case studies. They underscored how VIS4ML tools enhanced expert analysis and insight derivation. However, the true measure of VDAR's impact, whether the insight led to improved model performance, was evident only in 1/3 of the papers. And subjective user experience was prevalent, accounting for about 65.4% of the papers. This consisted of qualitative feedback, think-aloud protocols, and sometimes Likert-style surveys. Such observations mainly affirmed the tool's utility and hinted at potential enhancements, and in many cases, the papers were asking the same experts who had been involved in the design of the tool to also evaluate it. So overall, while VIS4ML evaluations offer a diverse range of approaches covering the taxonomy, they also spotlighted existing ambiguities in determining what makes an insight truly significant. Based on these findings, we can see that while many papers aspired for generalizability as indicated by the outer circle in this figure, current implementations and evaluation are somewhat scoped to a VIS4ML design contribution as indicated by the inner circle. Through our analysis of the results, we identified potential threats to generalizability of VIS4ML research. First is the ambiguous expertise characterization, in which assumed knowledge versus true expertise needed to use the VIS4ML tools are often mismatched. Therefore, we argue for greater transparency in specifying required expertise for a system is essential in VIS4ML research papers. Second is overfitting to specific cases. The dominance of hypothetical usage scenarios can lead to tools overfitted to certain data sets or insights, so tools should be validated against a wider range of scenarios for broader applicability. Third is constrained evaluation practices. As we mentioned, repeated reliance on a small pool of experts for both design and evaluation can bias the results. Fourth is postulating broader utility from limited exploratory evidence. Only 1/3 of the papers in our set offered statistics as evidence of model improvement through human involvement, while other tools mostly relied on post-hoc visualizations to make claims about utilities which have their limitations. And finally, papers don't always specify how much exploration or effort led to the showcased insights and examples presented in the papers. A clearer understanding of the effort required can gauge a tool's practical reproducibility. So in conclusion, we propose 3 recommendations for action. First, there is a need to enhance documentation in VIS4ML research, emphasizing the system's specific dependencies and constraints when compared to the generalizability needs. We recommend reporting hidden dependencies, ensuring clarity on datasets used, scalability limits, and user learning curves. This approach not only bolsters the system's authentic contributions, but also streamlines the research process for downstream research to practice transfer. Second, it's crucial to clearly convey the deductive reasoning behind every decision, from research motivation to study conditions. We should avoid ambiguous connections, and even when decisions are made for convenience, we argue that they must be transparent. And lastly, VIS4ML needs stronger ties with ML and HCI fields. As it becomes central to data science and human-centered AI, VIS4ML should prioritize practical adoption of the contributions, and to bridge the research with ML practice, deeper collaboration and effective knowledge transfer methods are essential, as well as addressing the challenges of replicating VIS4ML findings. Thank you for watching, and please check out our paper for complete details.